2.3 continuity, worked out problems. So find the points of discontinuity. Points of discontinuity. How do you want to write it? Doesn't really matter. Let's back to the bottom and set it equal to 0, x minus 3, x minus 1. So infinite discontinuities at x equals 1, comma 3. And then per the directions, continuous everywhere else. This is an absolute value. Graphs, there's no discontinuities. So no discontinuities. Continuous everywhere. Third root of 2x minus 1. Now, third root I can take anywhere. It's not going to cause any problems. Square roots or fourth roots or anything with the even number is a little bit of a problem, but there are no discontinuities. And it is continuous everywhere. And cotangent of x, do a quick graph of it, but I've done it before. So there are infinite discontinuities at y equals kx, so 0, pi, 2 pi, negative pi, where k is all integers. Should have a little more curve on it. And then it is continuous everywhere else. And then ln of x plus 1, I know you can't graph this whole thing, it's natural log. So we have an infinite discontinuity, because there's an asymptote. At typically 0, but this one's been shifted to the left 1. And then it's not continuous everywhere. It's continuous everywhere to the right of that. And this one's pretty cool. You definitely got to graph this. Plug in 2 over 2, we get 1. Plug in 0 over 0, we get a whole. Plug in negative 1, we get 1 over negative 1. You definitely want to know that one. Pops up a lot. So we have jump discontinuity at x equals 0, and it is continuous everywhere else. All right, so use the function to find to graph the piecewise below and answer the question. So let's see what we got here. X squared minus 1, so it does, I forgot. Including including. And then 2x, so not including, not including. And then just 1. And then from 1 to 2, negative 2x plus 4, plug in 1, get 2, plug in 2, get 0. Open dot again. Oh, I'm so impressed with myself. And then 0. So that's a line right here, which I'm going to have to make crazy thick so you can see it. And again, with an open dot at either end. Cool. So does f of negative 1 exist? Yes. And it's 0. Does limit as x approaches negative 1 from the positive side exist? Yes. Also 0. Limit as x approaches negative 1 from the positive fx equal f of negative 1. Yes. 0 and 0. Is f continuous at x equals negative 1? Well, we had that definition of endpoints, so yeah, I guess so. Most people would argue, well, no, but it doesn't go. Well, yeah. And, you know, fulfilled the definition, so. Does f of 1 exist? Yes, it's 1. Does limit exist? Yes. From the left and the right. Doesn't say left or right, so we have to do them both. 2. Do they equal each other? No. Is it continuous? No. But we're just walking it through the definition. Trying to make it as clear as possible. Is f defined at x equals 2? No. Why the exclamation point? I don't know. Is f continuous at x equals 2? It's not defined there, so no. And that's a very firm period. At what values of x is f continuous? Well, I would say it's from negative 1 to 3, except for here, here, and here, and here. 0, 1, 2. And I'm not including 3, so we will do this. Negative 1 to 3, except 0, 1, 2. What value should be assigned to f of 2 to make it continuous? 0. So f of 2 should equal 0. What new value should be assigned to f of 1 to make the new function continuous at x equals 1? So new value should be assigned. This was just a value. This is a new value. You can't do this. You can't replace something that's there. We could go and change the whole function, and that's what they're more or less asking. So f of 1 equals 2. That's a good little page of problems. Help people understand what's going on here. Find each point of discontinuity, which are removable, which are not. Yeah, now they're getting into that stuff I was referencing earlier. So let's graph. And let's go with discontinuity at x equals 2 and not removable. Because the limit as x approaches 2 from the negative side of f of x does not equal a limit as x approaches 2 from the positive side of f of x. It's cool writing that. Really makes me feel like I'm a tough guy. All right, 14. Okay, discontinuity again at x equals 2. They get the whole removable thing. Again, I don't like this, but fine. We'll call it removable, where we could redefine the function. Certainly nothing to get worked up over. And again, it's just all about definitions. Limit as we approach. That was pathetic. Limit as x approaches 2 from the negative side of the function equals limit as x approaches 2 from the positive side of the function. That's why it's removable. Notice we can put some pretty cool proof notation together, and calculus is used a lot in proofs. That would be one of them right there. Onwards. Got my colors wrong. I feel shame. Also don't know how to make an S all of a sudden. Discontinuous at x equals 1. Non-removable because it is an infinite discontinuity. And graph this one. And we have discontinuity. Jeez Louise. Discontinuity at x equals -1. Removable. We would just have to redefine f of -1 to equal 0. I don't really like this stuff. Give a formula for the extent of function that's to the infinite point. All right, this is how you used to find limits before we did lots of graphing. Let's see if I can remember how to do this. F of x equals, it's a perfect cube, so SOAP. I think I go with x1, x squared, x1. Same side, negative, opposite sign, positive, always positive. Would have bet a lot of money against me remembering that. All right, and that's our function. I'll get rid of the discontinuity. Plug in 1 now, you get the same thing. So whenever they say to, this kind of nonsense, it has to be factorable. X squared plus x plus 1 over plus 1. It's like math. Now, that's the cool way to do it. This is the ugly way to do it. We would say, oh, we can't plug in 0. Well, then let's do this. Let's define it piecewise. Sine of 4x over x, comma, x does not equal 0. And We know it's going to hit 4. I know calculus, so we will say 4. And if I didn't know how to figure that out, then just graph it. I'll show you everything in detail. Yeah. All right. Same deal. By the way, it's a talent being able to make a nice bracket. If you can't do it, I feel bad for you. And 1. And over here, oh, I love this little trick. So cool for knowing it. Multiplied by the conjugate, x minus 4, root x minus 2, root x plus 2, root x plus 2. Oh, by the way, if we plug in 4, root 4, 2 minus 2, we get 0 on the bottom. So we get x minus 4 root x plus 2 over x minus 4 kill equals root x plus 2. Playing with conjugates. Explain why the given function is continuous. There's an asymptote at 3, but on its domain, it is continuous. So yeah, we're not going to lose any sleep over this. I remember the first time I taught it, I spent hours on it, then I realized, I've been wasting everybody's time. So the domain is that, and then I would just say, since the function is continuous on its domain, it is considered continuous. Over here, domain is from 1 to infinity. Plug in 1, we get a 0 on the bottom, so we say everything but 1, but anything greater, because anything less would be the square root of a negative number. It doesn't exist except in a fantasy world. And then same reason as number 21. And just a little more definition, smithing. And a lot of people are like, can I just skip these problems? Like, yeah, if you really want, go ahead and skip them. I don't really care. All I'm saying is you should get used to blasting through these, even if it's just play with it for 30 to 40 seconds, look at the answer key and go, yeah, I got it. Yeah, and it's very ticky-tack kind of subject, this early calculus. Same deal here, x squared over x squared plus 4 is continuous. Tan x is continuous on its domain. Therefore, yada, yada, yada. So you're probably wondering, when will we be done with all this ticky-tack stuff? And the answer is soon. Soon. It pops up every now and then, but we're going to get into some serious calculus about 2 or 3 lessons from now. Good luck and happy mathing.